After several impasses and much discussion, Twirly Socrates and I have finally reached a resolution. This is the story. Now let's start this off with the opening question that I asked last time. Twirly Socrates, in F equals ma, do you agree that if m and a are singular, F should also be singular? Joe's mass times Joe's acceleration equals Joe's force. Not Joe's mass times Joe's acceleration equals their force. Or their force equals Joe's mass times Joe's acceleration. To that, Twirly Socrates' answer was...
F equals ma. F represents the vector sum of forces applied to one object. M is the mass of that object. A is the acceleration of that object.
Which sounds to me like he is saying it should be their force equals Joe's mass times Joe's acceleration, even if Joe isn't moving anywhere. So let's mix things up and try a different approach this time. Twirly Socrates, do you agree that how much force is applied to you should not change how much mass you have?
I agree. Forces change acceleration. They do not change mass.
Now let's check with Ben. Ben, do you agree that F equals ma has dependent and independent variables?
Sure, F equals ma has dependent and independent variables.
Ben, do you agree that in the formula that states force equals mass times acceleration, that m is an independent variable that is not changed by F or a?
In the context of classical mechanics, I agree that changing your acceleration will not change your mass. Theoretically, you could build a machine where the only thing you manipulated was the acceleration, and that would impact the rate at which fuel, mass, is burned, but that would be pretty convoluted. A pilot increasing thrust, which increases the burn rate of fuel, would cause F to change m.
Ugh, I'm sorry, but in that case, thrust would come from fuel burn, not fuel burn from thrust. In other words, that would be m changing F, not F changing m. Now let's go back to Twirly Socrates. Twirly Socrates, you claimed forces change acceleration. Does that mean you disagree with me when I say that me applying 1 pound of force to an elephant on the savannah isn't enough to cause it to accelerate?
Under normal circumstances, like in the savannah, friction forces are very strong. 1 pound will not be enough to move the elephant.
So you agree that not all forces change acceleration then?
I agree that not all forces perceivably change acceleration. If two opposing forces sum to zero, they do not experience a change in acceleration.
Perceivably. That sounds like he is mostly there with me, but isn't quite ready to let go of Newton's second law just yet. It is like a loose tooth hanging on by a string. We can do this. Now Twirly has some questions for me, to see if he can change my mind. Part of the fun of this game is it goes both ways.
Do you agree that it is possible to move an elephant with a non-zero force, provided there are no other forces competing?
In a frictionless environment, I don't see any problems. Yes, I'll agree with that.
When the ant pushes off the elephant, does the ant receive a non-zero force? Does the elephant receive a non-zero force?
Yes, I'll agree to that.
I say the above elephants have the same acceleration. Do you agree? One ant is pushing one elephant. Two ants are pushing two elephants.
Yes.
Do you agree that the acceleration of the elephant is proportional to the force? In other words, if there were 100 ants which simultaneously push in the same direction, is the elephant's acceleration 100 times larger to the one ant scenario?
As far as I can tell, yes.
If we were to place more ants on the other side of the elephant, do you agree that this would reduce the resulting acceleration of the elephant?
Yes, so long as they are in contact with the elephant, thus contributing to its inertia.
For example, put 100 ants on the left, and 33 on the right, and the elephant would move as if we had put 77 ants on the left?
Not quite. The group of 100 ants would win the contest with a difference of 67 in pushing power, not 77.
May I ask, what is it about F equals ma that you disagree with? From our common ground, we've established a. The direction of the sum of the forces determine direction of the acceleration. b. The magnitude of acceleration is proportional to the magnitude of force sum. c. The magnitude of acceleration is inversely proportional to mass. And that's F equals ma.
My issue is when F equals 0 because A equals 0. We spoke about that concerning the stalemated arm wrestle. Just because the arms are not moving doesn't mean there are no forces present. I'll also add, that is why I can't move any boulder I want just by touching it. A boulder can have forces acting on it without accelerating. It might work in a frictionless environment, but this is real life. If you want to change my mind on an issue, I suggest remembering what the issue is.
Would you be satisfied if we reworded it to say, the vector sum of forces acting on an object is equal to the mass of that object times its acceleration, F equals ma?
When it comes to the laws of physics, goalposts should be firmly established and shouldn't be moved around all over the place. Feeling the need to rewrite the law acknowledges a problem. I support rewriting bad laws. I'm not satisfied in rewriting it that way, though.
Do you agree with F equals ma if F and A represent a vector sum?
No. If I push on a boulder and the boulder doesn't move anywhere, it breaks the second law under that wording.
How is this inconsistent? The amount of force, the vector sum of forces, is 0, so m times a is 0.
I didn't push on it with a force of 0! Now let's try and refocus in on my opening question, because I feel like we've really gotten away from that. Do you agree that if m and a are singular, F should also be singular? It is Joe's mass times Joe's acceleration equals Joe's force. It is not Joe's mass times Joe's acceleration equals their force, or their force equals Joe's mass times Joe's acceleration. Let's go see what NASA has to say on that matter. They have a whole page here dedicated to Newton's laws of motion. And if we scroll down, they have the little thing at the bottom that summarizes Newton's second law of motion. Concerning the second law, it says the acceleration of an object depends on the mass of the object and the amount of force applied. Which seems consistent with the claim that it is Joe's mass times Joe's acceleration equals their force, even if Joe isn't moving anywhere. So, according to NASA, F is the amount of force applied, and when a boulder does not accelerate, it means it has no force being applied to it. By NASA's wording, the mass of the boulder and the acceleration of the boulder should tell me how hard I am pushing on the boulder. So when the boulder does not move, it says I am not applying any force to it when I am pushing on it. This is a big problem. But I will say, by NASA's description, it is saying the acceleration of the ball depends on the mass of the ball and how hard it was thrown, plus other factors like wind and gravity. So, I can concede that this can be described as their force. So long as Joe is being thrown by 2 or more people, their force equals Joe's mass times Joe's acceleration. I have no problems with that. However, after doing a little bit more digging, I found out that Newton's second law was not originally F equals ma. According to his book Principia, it was P equals mv. P here stands for momentum. So this is saying an object's momentum equals an object's mass times the object's velocity. Exactly why people felt the need to change it, I don't know. But this works for me, so long as an object that doesn't move has no momentum. Abolish NASA!